I'd like to introduce you to the FT4 Powder Rheometer. This is our flagship product for the measurement of flow properties of powders. We've been supplying it to industry for many years now, and also academia for research. It measures a whole range of material characteristics, principally powder flow, but the dynamic characterization of powder flow, so how powders behave whilst in motion. It looks at the effect of external variables such as strain rate, the extent of aeration, the extent of consolidation. But it also has the ability to measure traditional shear properties, wall friction characteristics, permeability, compressibility and density. So a whole range of different material attributes, which is necessary if you are going to fully characterize your powdered materials.
To understand how a powder behaves in process, it must be tested under conditions that simulate that process. The FT4 subjects powders to the types of stress and flow regimes that it will be exposed to in process and quantifies how it responds. A powder moves through a process as a bulk assembly and therefore should be assessed as a bulk assembly as well. FT4 measurements are influenced by all physical properties of the assembly and therefore provides the most comprehensive characterization of a powder. The FT4 is a precision instrument which generates repeatable, reproducible and reliable data. This is vital to any science. If data is not reliable, then it provides little or no value. It is highly sensitive and capable of quantifying and identifying minor differences between powders that are otherwise similar and aren't differentiated by other techniques.
Thank you for joining our webinar today. Today we're going to talk about the FT4 Powder Rheometer and how it can improve your yield in lithium-ion battery manufacturing. The FT4 is just one instrument in our portfolio that can be used in the battery market. Before we get started, I just want to introduce ourselves. I am Jeff Rivnak. I am the Vice President of Market Development and have a PhD in Chemical Engineering from the University of Delaware. I have over 25 years of diversified experience in the advanced materials industry and have 12 patents in various applications such as polymerization of fluoromonomers, nucleating agents for foams, as well as a framing structure for solar panels. In my last role at Solvay, where I was there for 20 years, I worked in various business development roles, including alternative energy, composite materials, as well as healthcare. In my last role, I helped to set up a new materials business that in the early stages of COVID helped to develop materials for ventilators, N95 masks, and face shields that help save countless lives. Nikki?
Hi everyone, my name is Nikki Monroe. I'm an application scientist here at Micromeritics. My background is in chemical engineering. I have a BS and an MS from the University of Delaware, specializing in powder rheology. And before this, I was involved in numerical techniques to predict bulk solids and powder behavior using discrete element method, specifically looking at particle-to-particle and particle-to-wall interactions and how they affect various stress distributions and bulk structures within powder beds.
Okay, before we get started on the FT4 and how it can be used in the battery space, I want to give you a little bit of an overview about Micromeritics. We've been around for almost 60 years. We have 3 production facilities, some in Europe as well as in the United States, and have over 330 employees as well as distributors around the world. The icon on the map that you see are the various applications that we are in. The position on the map is not necessarily where the application is. Some of them are chemicals, mining, as well as additive manufacturing and pharmaceuticals, and we're also involved in the sustainability industry such as green hydrogen, fuel cells, and batteries that we're going to talk about today. Our sales are very evenly distributed around the world. We have between the United States, Europe, China, as well as the rest of the world. And down at the bottom you can see all the areas where we lead, which is surface area, porosity, powder flow, density, particle size, and particle interactions. The reason we think this market is so important is the tremendous growth that is being predicted over the next couple years. In the upper left, you see a graph that shows over the next 5 years, the market's going to grow from basically 200 gigawatt hours to 1,000 gigawatt hours, so over 5x demand in those 5 years. This is going to translate into capacity growth, and it's already been announced in Europe, Asia, and the United States, over 1,000 gigawatt hours of new capacity, with Europe and Asia having very high growth rates over the next couple years. We're seeing the exact same thing in the raw materials space. In 2021, approximately 1 million metric tons of raw materials are going to be needed, growing to almost 4 to 5 million metric tons by 2025 and 10 million metric tons by 2030. This is to supply the graphite for the anode materials, all the elements needed for the cathodes, as well as various coatings for the different technologies. Within this market, micromeritics is already a key leader in this industry. On the left-hand side of this graph shows all the different papers and scholarly articles that are written within Google Scholar. If you search by micromeritics, batteries, and then one other element like anode, cathode, or lithium sulfur, sodium ion, you find thousands of references that are referencing our equipment used in these places. Then on the industrial side, we're already a strong player. We supply over 80% of the battery OEMs in this industry. We have over 200 current customers, and our growth rates are corresponding to what you saw on the last slide. In the last year, we've seen over 3x growth in this market space. The majority of the auto companies are already relying on our products for both R&D and manufacturing, and our products are also being used at every stage of the value chain, from raw materials, precursors, the electrodes, both the anode and cathode, separator, solid electrolyte, and then there's been a lot of news recently about recycling, and we're already helping companies do the recycling of their materials. This chart gives you a little bit more details about the battery manufacturing process in the center. So it starts at raw materials, goes to quality assurance, then you have the slurry preparation step, then you go to the coating, calendaring, and drying step, and then finally the cell slitting and filling with the electrolyte. Our equipment up at the top can help with every single part of this manufacturing process. What we're going to talk about today is we're going to focus in on the slurry preparation part and how the FT4 can help with this stage. We're going to talk about the wet process today, but there's been a lot of talk about dry processes recently in the news, and the FT4 is also a perfect instrument for that. So with that, I'll hand it over to Nikki.
Thank you. So the FT4 is a universal powder rheometer, which is designed to simulate a wide variety of processing conditions and environments that the powder could be subjected to during the battery manufacturing space or in any given process that uses a powder. The ways that we can characterize the powder using the FT4 and its rheology would be through resistance to flow and motion, its shear properties being shear strength or shear against material or equipment walls, as well as bulk properties such as the bulk density of the material, the compressibility of the powder bed, and the powder bed's permeability. Today, specifically on the battery front, we are going to be using the FT4 in order to improve the homogeneity of the slurries, to increase yield of the electrode casting, and to control batch-to-batch variation when producing batteries. So here's an animation that can show some properties of the powder and how they can influence the powder's flowability. Here we've got powders with high amounts of surface roughness that contribute to the particle-to-particle friction. And next we've got misshapen particles that are prone to high amounts of mechanical interlocking. And we can see that compared to their more free-flowing counterparts, these two characteristics can influence how the powder flows in a given process. So the different methodologies we can look at using the FT4 can be characterized into 3 different categories, being dynamic flow, bulk properties, and shear properties. The dynamic flow tests are all going to be subjecting the powder to a low stress environment and relatively high flow rates against each other. The bulk properties are analyzing the powder bed on a larger scale and looking at the more wide interactions between the particles and each other, as well as the shear cell tests, which are subjecting the powder to a high stress environment and characterizing the powder's onset to flow either against itself or against an equipment wall. Looking at each of the tests individually, we can see for dynamic flow tests, there's stability and variable flow rate, consolidation, and aeration. And while it's only a single test, the stability and variable flow rates can characterize a wide variety of properties about the powder, being things like specific energy, which is the resistance to flow in an unconfined space, flow rate sensitivity, which can characterize the powder's sensitivity and its behavior to different processing conditions, as well as basic flowability, which is the powder's resistance to flow in a confined space, opposite of the specific energy. We can also look at the powder's sensitivity to consolidation and how much its flow is impacted by the amount of free space between the particles, as well as the sensitivity to aeration, where we feed air in through the powder bed and can characterize how much more the powder is able to flow when it's subjected to airflow. In the bulk category, we can look at the powder bed's compressibility and its permeability, where the compressibility is the bulk density sensitivity to applied loads and normal stresses, and the permeability test is characterizing the powder's the particle and air interaction and how easily air is able to escape from between particles. Lastly, the shear cell analysis can characterize the onset of flow in a high stress environment by shearing a plane of material across itself or by shearing a plane across the equipment wall. The way the FT4 actually operates is by using this twisted blade and having it traverse through the powder bed at a fixed helix angle and tip speed. And as it makes its traversal down the height of the powder bed, we are going to be recording the torque, the force, as well as the height of the blade. So there's two ways that we operate the powder, or the FT4, when we are operating it in a dynamic test. The first step is the conditioning step, which I will go into more detail on later, but the gist of the conditioning step is that it is a preparation for the material in order to improve repeatability and create better reproducible results. Then when we rotate the blade on its flat edge, we are moving the blade in a more aggressive flow pattern and compacting the flow downwards as we rotate through the powder bed. We use this to actually report the flow parameter being flow energy, which is combined from the torque and the force measurements that we are recording as the blade makes its traversal. So for today, we are going to be looking at two tests in order to better characterize different batches of lithium-ion iron phosphate. Jeez. And those two tests are going to be stability and variable flow rates and permeability.
Okay, thank you, Nikki. So before we go into the details of how the FT4 can be used to characterize the lithium iron phosphate, just to bring it back to the batteries, Micromeridics has instruments that can help to optimize all the different components of a battery, so whether it be the separator, making sure you have the proper safety, or getting the proper diffusion through the separator of the lithium ions. If you're moving to a solid electrolyte, making sure you have the right particle size distribution to get the proper performance. And then what we're talking about today is the electrodes, so either the cathode or the anode, to make sure you get the best performance and be able to develop a specification for those. It can be used for both wet and solid processes. And today we're going to talk about a wet process where it was used to help develop the specification for lithium iron phosphate. So with that, I'll hand it back to Nikki.
So now we're going to move on to the instrument, and I'll show you how to perform a stability and variable flow rate test. And we can help interpret the data to better analyze different batches in the battery manufacturing process. So for this test, we're going to click Standard Test Methodologies, and you'll see the exact same screen that I showed earlier in the presentation. Then we click Stability and Variable Flow Rates, and the vessel size that we are interested in using. At this point, the instrument's going to prompt you to make sure that you have the correct vessel and blade accessory installed in the instrument. So I'm going to quickly install the 23.5 millimeter blade, as well as the 25 millimeter vessel for this test. This is going to be clamped in using this equipment that comes with the instrument. Then we check both boxes. At this point, the FT4 is going to ask you to tear the sample measurement so that we can record the actual mass of powder that's going into the instrument. And here we have some example material that we are going to be using today. At this point, you fill the vessel with the correct amount of material so that it goes above the split level. Then once the vessel is filled, you click Record Sample Mass once it's stabilized. Then it will bring you to a screen where you can record all the different information and labels about the data that we are going to be interested in for this given material. Then once you're happy with those fields, go ahead and close the safety shield and click Start Test. At this point, we're going to be running the conditioning step, which I mentioned before. So the reason why we actually run the conditioning step is because powders are very sensitive to their individual packing states, and the properties that we record of a powder's flowability are going to depend heavily on a given packing states. So it's very important that we have a nice homogeneous, evenly dispersed, loosely packed structure before we actually record any measurements that are done in the test. And so that's what the conditioning step is actually doing. We are removing any influence that I gave to the powder during its loading stage and gently displacing the powder so that it is homogeneous and will have much better reproducible data when we record the flow measurements. So once the FT4 has completed its conditioning step, it is going to prompt me to split the vessel, which means that I am going to open up the top clamp and remove any excess powder that remains on the in the vessel above the split level so that we can isolate a fixed volume of material, which I will do now. So once we split the vessel, go ahead and close it back up and lock it into place. At which point, we will close the shield and continue the test. For the sake of time, I'm going to end the test here because we have some pre-recorded data that I can talk about, and it will save us a good roughly 15 minutes while we let the instrument run. So when we actually run the stability and variable flow rate test, what we are doing is performing a cycle of 7 steps where we condition the powder, then test, condition the powder, and then test. The reason why we do this is so that we can characterize the powder in terms of its physical stability, meaning how sensitive the powder is to being tested in the FT4. And we can identify certain properties of the material such as attrition, agglomeration, moisture uptake, sensitivity to electrostatic charge, and a few other properties. And once we've completed the stability portion of the test, we do the variable flow rate section, where we are again conditioning and testing the powder. However, now we are adjusting the tip speed as we traverse through the powder bed. And thus we can characterize the powder's sensitivity to the flow rates and better understand how its sensitive to different processing parameters, such as tip speed. So for this example, we're looking at the effect of specific energy in a battery application. And the reason why this is important is because specific energy is used to characterize the powder in terms of its particle-to-particle friction and its mechanical interlocking. And the way that it does this is by measuring the flow energy during the upwards traversal, so that we can isolate those two interactions between the powder and characterize them in terms of that. So in this example, we've got 3 batches of lithium-ion iron phosphate, and the first batch performed the best, which we can see based on its lower specific energy, implying that it has the least significant interactions between the particles in terms of friction and interlocking. Thus, it yielded the most homogeneous slurry and had better yield in the electrode production. If we compare this to the other 2 batches, we see that they had greater effect of particle-to-particle friction and interlocking between the particles, which led to inconsistent performance and a lot of different problems in processing, such as blockages, downtime, and out-of-spec products. So now that we've gathered these data for 3 different batches, we can set criteria for future batches and identify whether or not they will perform well in a given process. So here, for example, since we were only happy with batch 1's performance, we can set a criteria of a given specific energy, and then we know whether or not future batches will perform well based on these data. So the next test that we are going to be looking at would be permeability. So again, I'm going to head back to the instrument. So just like before, we are going to be selecting standard test programs. Then under bulk properties, we click permeability. And once again, it's going to ask you which vessel size you're using, and then prompt you to install the correct accessories. In this case, we use the same blade accessories to start out for the conditioning step, but we need the smaller vessel size along with the aeration base, which I'm going to plug in now. Then the procedure is the same, where it asks you to record the sample mass after tearing. Then load the sample in, again above the split height. And once again, it'll prompt you to record the same data labels and information about the given sample that you are testing at a given, in a given test. So I'm not actually going to run this test again for the sake of time. Instead, we're just going to look at some pre-recorded data and use it to analyze the materials in a battery space. So what the permeability test is actually looking at is it's flowing air through the base of the powder bed and applying different normal stresses. And as it adjusts the normal stress applied to the powder bed, we are going to be recording the pressure drop from the air going across the powder bed. Thus, we can characterize the powder in terms of its air entrapment. We can better understand the particle-to-air interactions, and we can see effects such as the various packing efficiencies and response to applied stress in the powder bed. In different samples, we find that materials that have high permeability will yield a low pressure drop because there is less resistance of the air as it goes across the powder bed at a fixed speed, whereas less permeable material will have a high pressure drop going across the powder bed. So here we have the same 3 samples that we showed earlier, 3 different batches of lithium iron phosphates. And here we performed the permeability test on all 3, and we can better understand the differences between the 3. So we find that once again, batch 1 had the best performance in process, and we can see this in terms of its higher pressure drop or lower permeability. And the reason why this occurred is due to batch 1's more efficient packing and therefore the less capacity for the air to permeate through the powder bed, whereas batches 2 and 3 gave had greater void space and thus more volume for the air to pass through more easily. So based on these patterns that we see, we can better understand why batch 1 yields a more homogeneous slurry and has better production performance in electrode casting. And likewise, we can understand why batches 2 and 3 gave inconsistent performance and led to blockages, downtime, and out-of-spec products. So once again, as a demonstration, since we were only happy with batch 1's performance, we can set a criteria for the pressure drop that is yielded in this test, and then perform this permeability test on future batches to predict whether or not they will perform well in electrode processing.
All right. Thank you, Nikki. So today we gave you a real-life example of how the FT4 Powder Rheometer could help to develop a more robust powder specification to improve the electrode performance yield. However, Micromeridics has a lot of different instruments that can be used in the battery market. We have instruments that can help with the quality assurance and control in the manufacturing process. In the R&D, we can help to optimize all the different components of your battery. And then as the R&D is going to the next generation of materials, it can help to understand those materials better. On the right-hand side shows all of the things that Micromeridics leads in: surface area, porosity, powder flow, density, particle size, and particle interactions. And all of these techniques can be used to help improve the energy density, make sure your battery is safe, as well as improve the cycle life so you have a battery that lasts a long time. Thank you for joining us today. We hope to see you on future webinars, and we'll open it up to questions now. Thank you.
Thank you all for joining us today to discuss optimizing lithium-ion battery manufacturing. Now I'll open the floor for any questions you may have. I saw that we had some questions coming in earlier. I just wanted to remind everybody that if you'd like to keep your questions private, you can just put a P ahead of time and we will answer them afterwards in an email. So I'm going to go ahead and start with some of the first questions we have. This question will probably be directed more towards Nikki. How can we use the other FT4 tests to improve battery processing?
Hi, everyone. So we can use the other FT4 tests in a variety of ways to answer or to help improve battery processing. And I'll remind you that what we talked about today was specifically on the creating a homogeneous slurry for lithium iron phosphates. That said, there's plenty of examples of upstream processes such as storage of raw material, dry mixing, transferring the raw material into different containers. So there's definitely ways we can optimize those different processes using the FT4. But what we talked about today was just one example of a unit process and in the battery manufacturing. And it's important to remember that while it's good that we improved one unit operation, we can't consider that in isolation, and we need to think about the entire processing from raw ingredient to final product.
Absolutely. Thank you, Nikki. So our next question up, probably going to be coming to you, Jeff. How can micro products be used in the recycling of lithium-ion batteries? I know this has been a lot in the news lately, and that's what they pointed out. So can you touch on that?
For sure. You can think of the recycled materials is basically another starting material that you have. So all the instrumentation, all that is used for the raw materials are also going to be used for the recycling. So we have the TriStar that's being used for measuring the different properties of that, as well as the density is a very important measurement. As you're starting to get into some of the precursor materials, as the first question was asked, the FT4 could also be used to optimize some of those properties. The other thing that's important with recycling is many times people don't want to use 100% recycle stream, so this can also help our instruments can also be helped to understand what level of recycling that you want to use to still get the same good properties.
Thanks so much, Jeff. So next up, we have a question from Emmanuel. The question is, what is the advantage or the difference in testing rheology in slurries compared to powder forms? For example, coating or the electrode materials are in wet form. Why test in dry form?
I can answer that. So I would say the advantage of testing in the dry form is that you have an idea of the performance of the slurry after it's been wet before you actually cast it into the slurry. So you know a priori how the material is going to yield in terms of its performance once it's in the slurry, which can help you reduce wasted material, improve on better batch-to-batch variation before we even get into the slurry end.
And I'll just add to that what you said, Nikki, is an example we gave today. The three materials that tested looked exactly the same by the normal quality control procedures, and so until they looked at the FT4, they weren't able to see differences. And now they can actually have a specification that can then help them determine what raw materials will give them high yield performance in their electrode manufacturing.
Yeah, exactly.
So Nikki, going off of that, this is going to be a two-part question. So when you're running tests on the FT4, first of all, how much powder is actually required to run the test? And then on the back end, what happens when they struggle to interpret or make sense of the FT4 data?
So the first part, how much powder is required, is going to depend on the specific test you're running. For example, in the two tests that we looked at today, being permeability and stability/variable flow rates, you're going to need 10 milliliters of powder for permeability versus 25 for stability. That said, we also have special accessories for analyzing a wide range of volumes for powder, down to 1 milliliter and up to something like 250 milliliters of powder. So depends widely on your application and what material you're using, as well as which test you're running. And the second part of your question, what if we struggle to understand the data, or what if we don't know what it means? For that, I will say that we have a strong applications, not to toot my own horn, but we have a strong applications team made up of myself and some really, really talented scientists based in the UK. So we'd be more than happy to, help look at data, help you troubleshoot anything that has gone wrong, help customize or modify the test procedures to give you better data that you can make better sense of, or just help explain anything that you see that you don't fully understand.
Thank you, Nikki. So we have one more remaining question in the chat. If anyone does have any more questions, you can feel free to submit them now. Our final question will be directed towards you, Jeff. Where else can the FT4 be used in the battery process? Today we discussed the yield, but is there any other applications where the FT4 can be used?
Yeah, if anywhere where people have powders in their processes, lately in the news, it's been talking about some dry processes for separators. That could be, for example, a place where this could be used. And then as you go back into the value chain in the earlier stages with the raw materials and precursors, in those parts of the process, the FT4 can also be helped if you have powders there as you're trying to optimize your cathode materials or something else. So if you have a process and you need to have try to understand it better, our applications engineers, as Nikki said, can help talk through it and give you some examples of how we can help you to improve your processing.
Thank you, Jeff. So for all our remaining questions, we will email you shortly with any responses. If anybody else has any further questions, like I said, feel free to send them in, and I'll hand it off to you, Jeff.
All right. Thank you for everyone who attended today. If you have any specific questions about the FT4 or any of our other instrumentations, please go to the link that was shown earlier in the webinar on our website, and we can answer your question privately and help you improve your battery performance. So thank you, and talk soon.
Yeah, thank you all for your time.